Wait, what were you saying?
Me?
What else do we need?
Okay.
Oh, I was gonna say that we also should probably include the fact that it's on the ice surface, so there's not going to be any frictional force on the low or on the bottom box.
Okay.
By the
That's for
ground.
assumptions.
Oh wait, I didn't realize there's another. Okay, cool.
For principles, we're just doing friction principle and what was the other one?
I think that's it.
I just said equations of friction.
Okay. Well, okay, system is the top box.
Mm-hmm.
And then the surroundings, bottom box, and you and Earth. Neat.
Wait, is system? No, isn't system the bottom box?
We are just pushing the top box.
But we're observing the bottom one.
But we're applying, what the heck?
Can we just say system of two boxes?
What does everyone else think?
Sorry, what was that?
I think since they're not slipping on each other, I think it would be the top box and the bottom box.
Top and bottom, okay.
Since the box
The system is both boxes.
Okay, I'm good with that.
And surrounding is ice. And you.
Yeah, I
Okay.
agree.
You guys convinced me. Let's go, and then for solve the problem, the magnitude and direction of the friction force would be what, equal and opposite to the force that you apply?
Yeah. That makes sense.
Wait, did you say it would be equal to or less than or equal to?
Equal, directly equal to.
Can't it be? Oh wait.
No.
Frictional force or greater?
So, what were you gonna say? Because it'd be nice to have someone disagree.
Well,
No, I'm serious. Because like, if we all agree, then we're all just. I mean, one of us could just be wrong, and everyone's going like, "Yep, sounds good."
Well, because if you have the frictional force, it just has to be the frictional force just has to be greater than the force that you apply, right?
Right. So.
Yeah.
Yeah, if you want movement.
But the friction, when you push the boxes, the friction would be. Oh, no, it's not opposite. It's in the same direction. Because the friction is actually pushing the bottom box forward.
No.
So the friction would be equal.
I disagree. Okay.
You disagree.
So,
okay.
So basically, the friction is still counteracting. Because, okay, imagine the bottom box was not moving. And if you were pushing on the top box, right?
Mm-hmm.
Then the top box would just slide off if the friction wasn't in the opposite direction. Because there's no friction and on the ice, that's why the bottom one is moving. Technically, the friction is still going opposite of your force.
So
you know what I mean?
So if the only force being applied on the bottom box is the friction force, then how could it be that the friction is moving against your force and still pushing the bottom box forward? There's a contradiction there. I think there's actually I think the friction force is relative, and it depends on what you are observing.
Yeah,
If you are
it depends on
Yeah.
which box it is.
If you're observing the top box, then you are correct that the friction force would be acting against the force being applied. But since we are focused on the bottom box, which maybe that's our system, since we're actually, you know what, the bottom box probably is the system. Since we're focused on the bottom box, the only force being applied to the bottom box is the friction force, and the boxes would move forward together.
Sorry, this is hurting my brain. Hold on. So
No, I'm with you, Eric, on this one.
Neat.
it does say the coefficient. So we're looking for the coefficient. No. What would the magnitude and direction of the friction force exerted on the top box by the bottom box be in this situation?
Oh wait, on the top box by the bottom box. Oh wait, so
So wouldn't that be?
I'm so sorry. I flipped those around. I thought it was on the
Don't
bottom
worry
box.
about it. I was
by
thinking about something else too.
Okay.
So doesn't that change our system and surroundings?
Okay.
Yeah,
so
now our system
so-
would be top
Oh
box.
yeah.
system is top box. Surroundings is bottom box. And everything else. Right. So the friction of the oh shoot. Okay, then it would no longer be equal and opposite. It would be help me out, guys. What is friction? Shoot.
It's
can't-
constant times normal force.
Constant times normal force. Right. So normal force is mass times gravity. So the force of friction Q times whatever the normal force is, and the normal force here is what? That's mass times gravity. But which mass is times gravity? It would be
Your system. Wouldn't it be the top box?
correct. Mass of the top times
I just missed
gravity.
what you said. What did you say?
So the normal force is mass times gravity.
Yes, but positive. Mass times gravity is
Yeah, but
negative.
yeah.
Because,
So I was saying what mass to count here, and I didn't catch who said what. I think it was Elizabeth that said it was the top box because it's your system. Which would
we
make
don't have numbers, do we?
no. So
Okay.
it would-
Wait, so are you guys just doing like F normal equals mass 1 times gravity, and then doing F frictional equals the kinetic constant times mass 1 times gravity? Is that it?
Wait, why don't we
sorry, I
just
didn't
do
hear-
F equals? Sorry, where's? Sorry.
Oh, I was just
Continue.
saying that I didn't hear what she said because I spaced out.
You guys, what were you saying, Elizabeth?
Okay, so I just wrote down that. So we have that F normal is equal to mass 1 times gravity, and then F friction is equal to the kinetic constant times the normal force.
I was
Which is-
thinking static constant because they're not moving.
Oh, you're right, you're right.
Wait, why don't we just do? Since we use there's one in Newton's law. Like since there's like I'm sure there's some kind of definition in our notes that says somewhere the static friction will be completely opposite of our force.
F
But it's
F net is 0, isn't it?
Yeah.
Wait.
Yeah, it's because in a static system,
Hey.
the net force is equal to 0.
And then I think what's going on here is since the bottom box is exerting a force in the negative x direction, a negative static friction, the top box is counteracting by giving a positive x direction static friction, which therefore moves the bottom box. That probably didn't make sense. Hold on.
I think that makes sense. I'm just confused on when it says solve the problem.
Oh,
It's the magnitude.
we're when it says solve the problem, we're gonna have just variable names.
Which is what I did.
Yeah.
But
Here. Just for later if I started sharing, but obviously right now I don't have a lot, and what I have I'm going to change. So so because the net force is 0, and when we're only applying a positive x force, then that means friction has to be the negative x force that is equal to our positive x force, correct?
Yeah, because they have to add up to 0. Yeah, in the x direction.
And
yeah.
we know that it is constant, or we know that this net force is 0 because
they're moving together. They're stuck together. Right? So if they're stuck together,
right,
that means the net force has to be 0, I would assume.
Yeah, since it's not moving in any direction.
well, it's constant force, so you emit a constant force and nothing else is moving.
Yeah.
Okay, so that changes. We don't even need to worry about all that junk. So that means
So we literally, I think we can literally
it's
just
just
write
one line. Yeah.
F equals
MA.
friction. Right?
I'm gonna say the magnitude, and I'm just gonna restate the question.
Like that's what we wrote, right?
I'm saying the magnitude and direction of the friction force is equal and opposite to the force that is being applied by the person.
I'm gonna do that in my justify section. Do we have a we don't have a justify section.
Yeah.
Or no, we have it later.
Okay. So just to be sure, so our answer is the magnitude and direction is equal and opposite to the force being applied by you. Is that what we're settling on?
I mean, that's what I am settling on.
Does anyone have any objections?
No objections here.
All right.
Wait, what are we? Sorry. Like, it's been off for a second.
Ayush, my man.
Sorry, I have like 80 ping. Spikes up a little.
Oh, that's right.
So what did you say again? Sorry.
The magnitude and direction of the friction force is equal and opposite to the force being applied by you.
Yes.
Okay.
Okay.
Moving on. Part 2. That took us 20 minutes. Don't worry. So the largest magnitude of the force you could exert on the top box and still have them move across the ice without slipping on each other. This would be the static component times the normal force, right? What does everyone else think?
Is this for part B of it?
Part 2 of part A of part 2.
Okay. Yeah, yeah, I agree with it.
because all of these are about to be the same.
So if they're already stuck together and they're moving together, you don't have to worry about the bottom boxes, like frictional, like static friction, like exceeding that, like because you're just applying the force on the top box, so you're not concerned with like the frictional force on like of the bottom box. Like, does that make sense? Like,
Sorry, what is your question?
If you want them to be stuck together,
Mm-hmm.
and you're only applying a force on the top box,
Mm-hmm.
so obviously you're concerned with like the frictional, like inequality or the frictional force, whatever it exceeds. Do you have to be concerned with the frictional force of the bottom box at all?
So if you think of, try and simplify the situation a little bit to, instead of two boxes on top of each other, one box on the ground. And the question now becomes, what is the minimum amount of force required to move the box, or the maximum amount of force required so the box doesn't move. It's the same thing, because the bottom box, we're going to like pretend it doesn't move relative to the top box. Yeah, and so we can pretend that it's like the ground or something, and then the question becomes a lot simpler. So to find the maximum amount of force and have the boxes not move relative to each other, we would want to find the what the static friction force would be.
Okay, that makes sense.
I think someone tell me I'm wrong.
Because static, you don't. If you exceed static, it's gonna start moving. It starts becoming kinetic. But if you want them to, you want it to not slip on each other.
Mm-hmm.
So you want them to stay together.
So, and the force of static friction is mass times gravity times the static coefficient.
Yeah.
Okay. Great. Does everyone get that?
Yes.
Yep.
Does everyone agree?
Yes.
Yes.
Okay. Then we are going to move on to part B. And part B is, what is the acceleration of each box if you are pushing the top box and you are greater than the force we just talked about in the previous answer? What is the acceleration? So what is the net force if they're moving? Now,
Well, sorry, never mind.
I mean, given that we would know how much force it takes for the box to begin motion, it would the acceleration would have to be greater than that value.
So, it's weird. They switched it up. So instead of magnitude of force, they did acceleration. But maybe those are the same thing.
Yeah, mass is always the same. So higher acceleration basically means higher force.
Right, but I don't know what. I'm being a little contrary here, but whenever I see acceleration and constant force in the same situation, I'm inclined to say 0. But
no.
At the same time, tell me why it's not.
Okay, so if there were constant force.
Mm-hmm.
Actually, you know what? Now that I think about it. Okay, so if I'm thinking of I'm thinking about it in terms of the momentum update formula.
Mm,
So if we still
sorry,
had a F
yep.
net to plug into,
Mhm.
we would be increasing in momentum, therefore increasing in
okay.
velocity and
Okay.
acceleration.
It's constant velocity. That means no acceleration. Force is acceleration. So if there is a greater than net zero force, then there is acceleration.
Yeah.
So
Actually, you know what? Yeah, you're right. You're right.
since force is acceleration, well, force is mass times acceleration, so acceleration equals force over mass. So the acceleration of each box would be force divided by, or force, what, minus the friction divided by mass?
Yeah.
Yeah.
Hot. Okay.
And we could just have the same assumption systems and everything.
Don't we have to do this twice because we have to do it for each box?
Each box. Way to rain on my parade.
Sorry.
Yes, I would. That would be the implication.
Well, it's just static friction over mass, right?
Static friction.
Or,
Oh, wait.
It can,
Oh, wait. So the boxes slip on each other. If they're slipping on each other, the
is it even moving?
The accelerations are going to be different because the top box is going to be accelerating a lot faster than the bottom box
because the bottom box only has the kinetic friction force applied to it, right?
And kinetic friction. Oh wait, no, they both have the kinetic friction. I think they're the same.
The
I think you were right
accelerations.
with the. I think the accelerations are the same because you're just talking about.
Okay,
Wait,
so
by slipping on each other, what does it mean?
how much friction is there? If they're slipping, it would be the kinetic friction. So now there's kinetic friction between the two boxes. So the force on the top box would be the force applied by you minus the kinetic friction, because as Ayush said, kinetic friction would be working against the force. But the bottom box doesn't have the force applied by you, it just has the kinetic friction, and that would be propelling it forward. So I think the acceleration of the bottom box is the kinetic friction times the normal force, and the acceleration of the top box is the force minus the kinetic friction force.
Well,
Not
it's
sure.
not
Is
for
that
the second one. It's not times normal force because
sorry?
friction.
Friction force.
Yeah.
I'm not sure that I followed that, but maybe.
I'm not sure
if
I
you,
did
type
either.
It out, maybe
Okay.
I'll be able to. Because I think. I don't know. I was thinking that the accelerations would be the same, but in opposite directions, because that just means the bottom box is like decelerating because it no longer has the original force applied to it, and the top box is the one accelerating, and they both have the frictional force applied to them. Did that make any sense?
Trying to think about how to explain it, because if you try it in real life, it's gonna move.
The bottom box would move a little bit.
Yeah, the bottom box will still slightly move.
But
yeah, but it's not accelerating.
No, technically it is.
Well, it's
Compared to last.
It's accelerating in the negative direction.
That would imply at rest, if you push the boxes, the box would go backwards.
But if you're moving at a constant velocity and you push the boxes, that one's just gonna slow down, right? And the other one's gonna speed up. Maybe not.
We have to assume no friction on bottom. So any force applied to the bottom box will be sort of like space physics. So like when you're in space and you touch something, it just goes forever. We have to assume that for the bottom box because it's on ice for some reason.
Okay.
So so if there's a negative acceleration pushing the box backwards, I don't
Well, it's not
think
moving. It's not moving the position backwards. It just means it's slowing down from the original velocity.
But
I guess at rest it doesn't make any sense.
Right.
Just go back to what Ayush was doing, and I'll see if I can.
Yeah, I just did acceleration equals. I did acceleration equals kinetic force over mass, too, like the mass of the big box.
You can. Okay, this is a dumb, whatever experiment, but I placed my finger on like my notebook, and I pushed the notebook across the table, and then I like lightened my grip so that way my finger was sliding over the notebook. The notebook was still sliding across the table, even though there was sliding forces between my finger and the notebook.
Yeah, I just did the same thing with my phone.
Yeah.
If like my phone is slowly sliding off, my notebook is still slightly sliding. And because this is ice, it's like zero friction.
Yeah, whereas the table has a lot of friction.
To move.
So that's just a real world experiment. I don't know, like it's just a proof of concept. But
yeah,
I'm fairly certain.
Maybe if you think about it upside down. Okay, just think about if you think about the bottom box as a system, and a force on the very top plate of the box is pushing it in the positive x direction, right? And that's being caused by you trying to move. So okay, sorry. Okay, imagine the box is upside down, first of all. Right?
Yeah.
And you're trying to move. If you're trying to move, if you were looking at it like regularly, you're trying to move the top box, right? If you turned it upside down, it would be the same thing as trying to move the bottom box on top of the top box, right?
I think I kind of get it.
So like you're trying to slide them. So if that's true, then you would be experiencing the kinetic friction. The bottom box would be experiencing static friction from the top box while you were trying to slide it. I need to visualize it somehow.
Okay, yeah, I think I kind of know what's going on. I think I get it now. Thank you, guys.
Okay.
Are you sure?
Yeah.
We could try explaining it a different way if you want.
I'm pretty sure I get it. Just let's start writing out the equations, and I think that'll probably help me understand it more.
Right. Okay. So the equation, I guess we have to split it into top and bottom. So the top box, the force would equal, or I guess acceleration. So acceleration equals the force divided by mass. So force of the top, that would equal, oh gosh, I'm forgetting now. That would equal U minus, so the force of U minus the force of kinetic friction. Or I guess we can just put force of friction. And then we'll calculate force of friction in a sec. So the force of friction is the coefficient of kinetic friction times mass of the top times gravity. which would imply that the force of the top box equals force minus the coefficient of kinetic friction times the mass of the top times gravity. And to get acceleration, we divide that all by mass.
The mass of one, right?
The mass of the top. Well, right now we're just looking at the
I have
top.
one as my top, but yeah.
Oh, I didn't show all that. I just wrote down.
Yeah, I'm just
I think it's better to do that maybe.
Maybe, I don't know. Oh wait, or no, never mind. But right, so that's the acceleration of the top. The bottom box. Okay, sorry. I'll wait until. Do we have all the top stuff written down? By the way, I'm sharing my screen with you guys if you want to.
Yeah.
Check. Yeah. Check. Mm-hmm. Whenever you guys are done with the top, let me know.
I'm ready.
Yeah, I'm ready whenever you guys are.
Chris? Chris? Did he fall asleep? Okay, we're gonna pretend like he said yes. Chris, you there? Oh. Nope. Okay. So anyway, bottom box. Bottom box would just be the force of friction divided by, here is where it gets tricky. Do we take the mass of just the bottom box, or we do the system, like top and bottom?
Just the bottom box.
Why?
Well, because we don't need to worry about friction first of all, so mass doesn't matter. Then we're only worried about the friction because we're only worried. Okay, how do I phrase this? The only force the bottom box is experiencing, the only thing it has to do with the top is the force of friction from the top box.
Oh, okay.
Sorry,
So,
I'm explaining this really badly.
No, you got it. I think so.
Right, because it's the only thing the bottom box has to do with the top box.
Oh, and the force of friction is the exact same.
As for the top box.
Yeah, as for the top box.
It's less than before, but it's still the same.
What?
It means the acceleration is less than it was originally, but it's close. Is that what you meant?
Yeah.
Okay.
It doesn't have to do with anything we're doing right now, but yeah.
I'm 100 plus.
Ah, Chris is back.
Sorry, I went to say something to my roommate.
You're good. We're finishing up part B, or section B of part 2.
Okay.
I don't think you missed much.
No, I got it.
Oh, by the way, we need to. We have to highlight and circle the final answer. But the. Did we write down system and surrounding?
It's the same thing. Oh no, never mind. It's different.
Well, there's two parts to this. So I'm going to put both boxes, and then the top as the system, and then the surroundings, I'm going to put the top box. It's going to look weird, but... It's just because there's two parts. Hey, did you guys get a grade for the recitation, for the previous recitations?
I started getting mine.
I did for like 2 of them. I think.
Yeah, I know. And then
I just think they're not graded yet.
Yeah, I know, but I want to. I'm worried that the video didn't go through. I have the video. I posted a link to the video, so I feel like it should have gone through. But
If there's a problem, I think they would let you know.
I don't have that much faith in this class. I was gonna wait a little while longer and then email and ask. If we don't have any grades, probably by like the end of this week, I was gonna email just because I figured they might be behind, but I have no clue. Or unless you guys think I should email earlier, because none of us have grades.
I have grades for the first 2.
Yeah, I have grades for the first 2 as well. It's just yeah. Ooh, someone got a text.
By the way, for surroundings, for the first one, for part 2A,
2A. Mm-hmm.
ice is not required. Ice doesn't have to do anything with ice.
Yeah, but not. I really don't think ice is a surrounding on any of them because the ice doesn't contribute any force.
Oh yeah, any of them. It doesn't have to do anything with. And then also for B, U isn't a surrounding. Because only the top box is exerting force technically.
But for the U, F applied is from U. There's 2 parts to this technically. I'm kind of grouping them together because I'm lazy.
Okay.
Now they construct an argument. I hate this part.
Should do this electronically. I don't like writing all this out.
Yeah, I've started just typing it all so I can save it as a PDF and upload it immediately.
I'm on my desktop, so I don't have like a 2-in-1. Can't like write on my screen. So it's kind of inconvenient uploading pictures.
Yeah. Oh, if you do like Google Photos.
Oh wait, yeah, I can use that. My Google Photos is
like it'll just automatically upload, and then you can just go to, yeah.
Yeah, it takes a second though, because like the pictures are. Gotta turn down the quality of pictures.
Okay, so we use the equations for magnitude, or the equations.
Are you on? Wait, what are you on?
Friction. I meant to say friction.
No.
I'm on the justify your solution and construct an argument part. So we use the equations for friction to solve for the forces, and then we use Newton's second law, F equals ma.
Yeah.
Okay, I'm sure we can do the next problem pretty quickly, hopefully. This one was just a bit confusing in the conception.
Don't read over the other parts to the justify section. It says explain briefly how the rate of change of momentum is related to the force you exert on the top box. And then it also says create another problem in a different context.
Yeah. The whole idea of like putting friction on something leads to the thing that has friction on it is moving. Sorry, I can't talk today.
Okay.
The rate of change of momentum what? I'm brain farting. Someone fill in.
Isn't it equal to, because F net is equal to the rate of change of momentum.
Right, there we go.
So,
wait, but the
yeah.
forces you exert on the top box.
So then you just, the rate of change of momentum is just subtracted from, or the rate of change of momentum is F net, and then you subtract your force, the force that you apply to get the friction.
Neat. And a different problem.
It asks. Okay, so what would be a similar situation?
Probably just a box on the ground. Find the minimum amount of force required to push a box on a table. Physicists love tables and boxes. And while we're finishing that up, I'm going to try and find the
I can just send a photo. It's in the last one. The last video.
Thank you.
Yeah. At the very last part.
Nice. Lecture
No.
9?
No.
Bruh,
Never mind.
you lied to me.
Sorry.
It's not even in the last
Maybe
video.
in the middle?
Oh my god.
Oh, it's that one.
It was the
Has to be.
second to last one.
There we go.
Bruh.
Okay.
Are we allowed to just use this as the... Because I totally am.
Yeah, no, we can use it. Why not?
Alright, this right here.
Oh my god.
Are you watching me just...
I'm so... I am not doing this on military video.
This is epic. Look at that. Do you think she'll recognize it?
I don't know.
Looks a little familiar.
Wait, is that green F net?
Dude,
Yeah.
I have no clue.
Yep.
Say F net.
Oop, I went to the next video. So
Oh, I guess it's blue.
the blue is the... What is this if there's a constant speed? Like if it's not slipping is blue. Green is if it is slipping. There. So, come on guys, fill me in. It's been a while since I've seen the lecture.
Did you say?
What is the...
I had to go for a second.
Alright, we're gonna continue.
Okay.
Principles and concepts. We need... Or are you guys still drawing? Hello.
Hello? Why did my voice not register? That's weird.
Okay, I can hear you guys now.
Okay. Yeah, so principles and concepts. Momentum principle, but I don't know what it's.
I think it's the
about.
friction principle. Newton's second law? Are we sure it's the second law?
Yes.
Okay. And
Momentum principle. It asks for the momentum at a certain point.
okay. Assumptions. No air resistance. And
Do we have to divide the net force into parallel and perpendicular components?
I hope not.
I hope not too.
Wait, no, I think we may. Right. Well, let's just try this. So system is the box.
You mean the block?
What is it? Is it a... Yeah, you're right. You're right. I just didn't read it. Block. Okay, so the system is the block, and the surroundings are the rotating bar and Earth. So the block's speed is a constant 3 meters a second. Alright guys, we need to solve the problem now.
Okay, this is gonna be my weak point. Let's see though. I don't know if I exactly understood this lecture.
Yeah, same. But that's what we're all here for, and we're gonna work through it until we get it done, which hopefully won't take too long.
I believe.
So we know that we don't have to worry about the parallel because it's at a constant speed, so that needs to go in our assumptions.
Oh, constant block speed.
Yeah, so no parallel.
But counterpoint. Never mind.
That was a strong one. That was a strong point.
You know, I
Good point,
Pull me
good
away.
Uh,
There.
I was like, I'm literally reading off of the lecture.
Right, so I forgot
funny.
that a parallel force would increase the speed, and this is only increasing direction or changing direction.
Yeah.
Yeah. Sorry, I am brain dead. I started my exam at like 11 this morning and have not stopped doing it since.
Dude, you are fine. But I will need you to contribute by doing all of this problem.
Thanks.
I got you guys. Look.
Remember when I usually was like, oh, we'll be able to do the second problem pretty fast.
Thanks, Ayush. Giving
You're welcome.
giving us hope that we didn't deserve.
So where do we start?
Okay, so we need to realize that the only force being applied is a perpendicular force, which is towards the center, and that is because the
Normal force.
yeah, the normal force, and that is because the only thing that is changing is the direction. The speed is staying constant. So
Yes.
the magnitude and direction of the rate of change of the block's momentum is the net force in the direction of the center. So
Perpendicular, and that is equal to mv squared over r.
Oh, look at that. Miss
Okay.
Lecture.
Intellectual.
mv squared over r. So r, look at that. Okay. R is 0.5.
I got 100% on lab 4.
Dude, nice. I've not been looking.
Okay.
Wait, don't
Sorry.
we all get the same grade for lab 4?
Oh, yeah.
Yeah.
Awesome.
So we all got nice.
Cool.
Okay.
It's like our
So-
brains are the best.
Yes.
Yeah, definitely.
Well,
I was talking to someone else. He said like his group would wait till like the last minute or something to do all this stuff.
what just
They
happened?
wouldn't even record.
Guys, help.
That's horrible.
Okay.
What?
Oh, that does suck. I accidentally
Those are
turned on
exciting.
Windows magnifier. Anyway, that sucks. Do they, like, for the recitation of the lab?
Like, okay, so like they refuse to like record it, and then like they'll use the discussion board over recording, and then like they wait like really late to do it. So like there's nothing to comment on and stuff like that. I don't know.
Right. Yeah, which is kind of like that's not really well, it's partially a flaw in how they're doing it, but at the same time, that's a flaw in how the assignment's designed, because like we could
'Cause if you-
sabotage each other so hard if we just
Yeah.
waited till the last day to do everything.
Sabotage time.
Right, guys, I got an exam this week. Don't worry about your grade.
E squared over r. P per equals, what is that? 0.1 times 9 divided by 0.5. Wow, this is terrible.
Which is 1.8.
Yes. I concur.
1.8.
Ooh,
I'm gonna trust
is
your
that-
math on that. Wait,
I used a calculator, so I think it's pretty trustworthy.
sorry, we said point. Right, I'm dumb. Okay, so 1.8, that is the... Get out of bolded. That is the magnitude of the force, and the direction of it is in towards the center. .8 newtons.
Oh wait, never mind. I said kilogram meters per second squared,
Bruh. Okay.
but I guess technically it could be newtons because it's the force.
No, you're right.
I was just taking it as a change in momentum.
Wow, okay. Typing what the heck?
Wow.
Meters, we're just gonna put squared per second. There we go. Nice. Do we have to be more specific with the direction? No, because it just gives us an arbitrary point. Now, what is the magnitude of the net force acting on the block? What?
Wait, did we calculate
hold on
part two
here.
just now?
What is a magnitude? Okay, part 1 was
What?
magnitude and direction.
Of the rate of change.
Rate of change.
So we calculated part 2.
Wait, but the rate of change is the net force.
No, we take the net force that we just solved for in the perpendicular, and I think we have to do something with friction. Did they give us anything for friction? Maybe we just say they're the same.
No, but if you look at the diagram that she drew, the net force of the who's getting Discord stuff?
Is it me?
Oh, okay. I'm not mad. It doesn't matter. So because the speed is constant, the parallel force. No, you're good. It doesn't matter. The parallel force.
Look, it's fantasy football. It's not as important as physics.
God, you made me lose my train of thought. Anyway, so
Sorry.
because the speed is constant, the parallel force is 0. That's in the slides, and so that only leaves us with the perpendicular component, and the perpendicular component is mv squared over r. That's the net force. So what the heck? The rate of change of the block's momentum. What is the change in momentum? That would also be... Okay, so just going back to the momentum principle. Momentum equals momentum plus F net times delta t, right?
Wait, say that again.
Yeah.
Yeah.
Initial momentum plus F net times delta t.
Right. So the rate of change in momentum is equal to F net. Oh my god, it's even on the slide. It literally says the change of momentum is equal to F net.
Wow.
So,
Love
wait.
it a lot.
So does that mean we just finished problem 2? Oh wait,
Yeah.
part
Wait,
1.
does it give us anything for friction?
Hit.
Would be the one
What
thing.
the heck? Okay, so friction, the change in momentum for friction, if you think about... actually what's funny is... Sorry, I got distracted. I'll answer your question. They don't actually give us a spot to solve part 2. Never mind. Anyway, sorry. So friction is canceled out by gravity? What the heck?
The horizontal or the component of gravity, is that what you mean? Force of gravity? The
Yes.
horizontal component?
Yeah. Thank you. Thank you.
Oh, since it's a constant speed, it's gonna. So the only time that friction would change is if it was a non-constant velocity. Okay. Cool.
Which is going to ask us about. But what the nuggets? That means that part 1 and 2 are the same unless we're crazy.
Wait, so why did we get kilograms per meters per second?
Oh wait, if it's F net. Oh, the change in momentum is newtons. Because the change in momentum is F net.
Yeah, I think those are equal to each other. I think kilogram meters per second squared is newtons.
Yeah, never mind.
No.
Kilograms meters squared per second.
Part 1, the answer is kilogram meters per second. Part 2, the answer is newtons. Anyone with me?
Yep.
I'm with you.
Are we actually going to put newtons for the second one? I don't know. I might just, because I find that hilarious, but the bar for what's funny is very low at this point. So we're going with 1.8 or 0.7?
1.8. Sorry.
Okay. Just to confirm, what are you guys putting as your answers for part 1 and 2?
Wait, the same thing, right? 1.8.
1.8, and then for units, or what are you putting 4
The
units.
same as you.
Oh, really?
I'm looking at yours right now.
Do you have newtons in the second part and then
Yeah.
kilograms
Yeah.
per second squared?
I was
And
just
then
kind of.
towards the center for both.
Oh, right. Yeah.
Oh, we have to write that.
I was just kind of memeing, but I'm okay with this.
Oh wait, we also need to create another. Okay. So, in words, construct an argument to explain and justify your solution. I feel like that one's pretty self-explanatory.
I'm just going to say the rate of change in momentum is equal to the net force since the parallel component is 0 due to the constant speed of the block. Cool. Now for part 2 of the justify section, if the block speed was increasing, how would the magnitude of net force be?
Wouldn't it be greater?
Yeah.
No.
What?
Yes. Yeah, it will be.
What a
The
turnaround.
internal dialogue I hear from you.
I wonder what the TAs will be thinking when they hear this.
I don't think they're gonna watch this.
I hope they watch it.
I hope they do too, but like, God, imagine if you were a TA. That would suck to watch this.
Hi TA, how are you doing today?
Yeah, hello.
This is Christopher Patchen.
Wait, yeah, if we should
Give
say
me
in the
100%
video.
and give my group 100%.
Yes, please. I
I would like to
that.
report Eric
What's
for stealing shoelaces.
What?
I heard about that on the news. I saw it on CNN.
I gave the shoelaces back.
Did you steal them?
Never did.
Still listen to him. Okay, back to physics. We're so close to being done. If the block speed was increasing, the magnitude of net force would be greater than what it was before. And the direction would be what, pointing forward a little bit? Pointing more forward than
in the direction of velocity.
before.
Like,
Oh, yeah. That's
more toward the direction of velocity.
yeah, I like that phrasing better. Than before. That is awesome. Create another problem.
Oh wait, slow down.
No problem.
I'm still writing that whole thing.
No, you're good, you're good. I forget sometimes that typing is faster than writing.
Should we just change the object that's on? It's being spun around, or we can do the water bucket one.
This time.
Or we can do a water bucket. You know, like the where you spin around a water
yeah.
bucket.
Instead of a vertical, do the sideways one. Do the
Oh yeah.
the circus ride. Circus ride. Force required to keep you from falling. I have no clue how to solve that, but we're gonna say that way we're not doing it like just a different object. Guys, help me out. How do you spell circus?
CRCOS, I think.
C-U-S. Oh yeah, you're right. I spelled circuit.
You're on word. You have auto spell, auto whatever. Check.
Oh yeah, you're right.
Autocorrect.
I forget what that's called too.
What is that ride called? Horizontal circus spin ride?
Circus? Ferris wheel?
Circuit? No, the The one where you kind of stand up against the wall. It was in lecture.
Zero gravity?
You stand up against the wall, and then it spins you around, and then you get pushed against the wall for some reason.
Did you say amusement ride?
Just spinny amusement ride.
Nauseous amusement ride.
There we go.
Boom.
Okay, I agree to this problem, this solution.
Blue. Yeah.
So I'm gonna start scanning this.
I also agree to everything that we did.
Hold on, everybody.
Oh,
Wait, can you scroll down to the bottom again? real
yes.
quick, So I can just check my answers.
So this is the
So this one.
yellow is the we got 1.8, right?
Okay, well I'm checking my reasoning and things.
Oh, okay. That would be right here.
Pointing more towards direction of velocity than before. Okay,
And
yeah.
I'm just gonna scroll.
then-
I'm gonna scroll up. Do you see this green?
Yeah.
The green is part 2 or part whatever. It's the green is if you're increasing in speed. Do you see how it's
Yeah.
pointing a little more towards the direction of movement?
Yeah.
Mm-hmm. Okay. Now,
And then the last one.
the last one, I'm just saying a
keep-
horizontal circus spin ride. What's the minimal net force required to keep people from slipping downwards? Oh, we have to say how is it similar? Ah, poop.
I just scanned it. Okay.
It is similar because cool. I'm going to stop recording now. Everyone say bye to the TA.